In this video, we're going to look at some more involved examples of calculating probability distributions. Imagine we have this scenario where there's a frog and two sides of a river. The frog is on one side of the river and that frog wants to reach the second side of the river. There are 3 lily pads in the river that they can jump on to reach the other side of the river. But the frog jumps randomly. So in this case, the frog, when he's on one shore, will jump to any of the destinations in front of him with equal probability. So jump to the first lily pad with probability a quarter, the second lily pad with probability a quarter, and so on. Whenever he's on one of the other lily pads, the same happens. The frog will jump to any of the destinations before him with equally likely probability, and so on, and so on. What is the average number of jumps the frog takes to reach the other side? In order to do this, we're first going to work out the PMF, and then we can use our expected value formula to find the average number of jumps. The frog jumping to the other side can be thought of as a sequence of jumps, and again, like our coin flips, we don't know how many sequences there are. But a good tool for sequences of events is probability trees. So when the frog is on one side of the river, it can jump all the way to the other shore, or it can jump to lily pad 3, lily pad 2, or lily pad 1. And it does this with probability a quarter for each of these. If it jumped to the shore, it reaches destination. There's no more jumps. If it jumped to lily pad 3, then it can only jump to the shore. And it does that with certain probability. If it jumped to lily pad 2, then it can jump to lily pad 3 or the shore. And there are 2 options in front of it. So it'll jump to the shore with probability a half, and lily pad 3 with probability a half. If it only jumped to lily pad 1, then it has quite a way to go. So it can either jump to the shore, to lily pad 3, or to lily pad 2. And there are 3 destinations in front of it, all equally likely. So I can jump to the shore with probability a third, and the other lily pads each with probability a third. Now think about the next jump. In this case, it reached the shore, so there's no more jumping. In this case, it reached lily pad 3, so it can only jump to the shore. And it does that with certain probability. Here, it's at the shore, so there's no more jumping. Here, it reached lily pad 3, so it does that with certain probability. And here, it still has 2 destinations in front of it, either the shore or lily pad 3, equally likely with probability a half. And finally, here, it can only reach the shore with certainty. Now let's think of all those end probabilities. What is the outcome that we care about, which is the number of jumps, and what is the probability of that outcome? So here, it reached the shore in 1 jump, and that the probability of that outcome is multiplying along the branches, which is just a quarter in this case. Here, it reached the shore in 2 jumps, and it did that with probability a quarter times 1, which is a quarter. Here, it reached the shore in 2 jumps, and it did that with probability a quarter times a half, which was an eighth. Here, it reached the shore in 3 jumps, and it did that with probability a quarter times a half times 1, which is an eighth. Here, it did it in 2 jumps, with probability a quarter times a third, so a 12th. Here it did it in 3 jumps, probability a 12th. Here it did it in 3 jumps with probability a quarter times a third times a half, which is a 24th. And here finally it did it in 4 jumps with probability a quarter times a third times a half times 1, which is 1 over 24. Now each of these outcomes are mutually exclusive. They can't happen at the same time. But some of those are the same outcomes. So let's just take each possible outcome in turn. What is the probability that the frog took 1 jump? There is only one of these outcomes which corresponds to 1 jump, so that is a quarter. What is the probability that that frog took 2 jumps? Well, 3 of these outcomes correspond to 2 jumps, and they are all mutually exclusive. So if it took either this outcome or this outcome or this outcome, we can add up the probabilities. So that would be a quarter plus an 1/8 plus a 12th. And doing the fraction manipulation there gives us 11 over 24. The probability of it jumping in 3 jumps, then there are 3 outcomes, this, this and this, all mutually exclusive, so we add up the probabilities. So that's an 1/8, add a 12th, add a 24th, and that gives us a quarter. And was the probability did it in 4 jumps, only 1 outcome, that is 1 over 24. We wanted to know the expected number of jumps the frog takes, so from this PMF we can take the expected number of jumps is the value times the probability of that value and sum them up. (50 over 24), which is about 2.083. We can double check we did this correctly by running a Monte Carlo simulation. So here I'm going to set up a spreadsheet where I'm going to run this scenario. There are 4 possible outcomes because there are 3 lily pads on the show. I've said that the theoretical probability of reaching the shore in 1 jump was a quarter. In 2 jumps was 11 over 24. In 3 jumps was a quarter. And in 4 jumps was 1 over 24. So we would expect these probabilities to come out. Let's set up our scenario. So the first jump, the frog can jump to any one of lily pad 1, 2, 3 or the shore. And I'm going to label those 1, 2, 3 and 4. So that is going to be round between 1 and 4. For the second jump, if they'd reached the shore, which is when they landed on number 4, they're gonna stay where they are. But if not, they're gonna jump anywhere between where they are plus 1, the next one along, and the shore. They're going to do that for each of the possible 4 jumps. We know we can't take any longer than 4 jumps. Let's just show a couple of rows of this to make sure we've got our logic right. Oops. So you can see here they jumped to lily pad 3, then 4 and remained at 4. Here they jumped straight to 4, Here they jump to 2, then 3, then 4, and remained at 4, and so on. So we're kind of doing okay here. Out of this, how many jumps did they do? So if there are 4 4s here, then they jump to the shore in 1 jump. If there are 3 4s here, then they jumped to the shore in 2 jumps. If there are 2 4s, then they jumped in 3 jumps, and so on. So that is 5 minus how many 4s there are. Again, let's just check we've done that correctly. So in this case, they jumped straight to the shore, so they did it in 1 jump. Same here. Here they jumped to 3 and then 4, so they did it in 2 jumps. Here it was 3, then 4, 2, 1, then 3, then 4, so they did it in 3 jumps. So this is, the logic is sound here. Let's run a lot of these. Okay, I've landed on 1,810 simulations. Okay, I've run a lot of these. Let's go back to the start. So now what is my probability estimate for the outcome 1? So that is going to be how many of this column are 1 divided by how many trials I had, which was 1810. And I can do this to each of those. Instead of 1, I can do 2, 3, 4. And you can see that our simulated probability estimate is very close to our theoretical now. So I think we've probably worked out the theory correctly. Let's look at one more example. So now we have a casino game. The game is played with just these cards, the ace of clubs, 2 of clubs, 3 of clubs, and so on. It's just these 8 cards. And the rules of the game, you draw 2 cards. If you get 2 hearts, then you don't score anything. If you draw 2 clubs, then your score is the smallest value of the cards you drew. If you get 2 of the same value, for example, a 3 and a 3, then you double the score. You get 6. Any other combination of cards, you score whatever was on the heart. So now we want to know, what is the PMF of this and what is the average score? To work out the PMF of this, we can do exactly the same as when we worked out the sum of 2 die. We're going to list all possible outcomes for the first and second card. So the first card can be the ace of clubs, 2 of clubs, 3 of clubs, 4 of clubs, ace of hearts, 2 of hearts, 3 of hearts, and 4 of hearts. And the same for the second. I'm just going to split this up again to make it a little more readable. And now, what is the score I get for each combination? Well, if I score 2 hearts, I'm in this quadrant down here, and I score 0 points. If I have 2 clubs, I'm in this quadrant up here, and I score the smallest value. An ace has a score of 1 here. If I get 2 of the same value, I score double. So that's 2 aces, 2 2s, 2 3s, and so on. So if I double the value, I'd get. Otherwise, I score the heart. So when I'm in this quadrant, when my heart is so they are all possible combinations, except I can't draw the same card twice. So any combinations which are on this diagonal are not possible. Now, except for those values I've just said are impossible, all other values are equally likely here. So just like the die, I now need to just count up how many of each value of there divided by how many possible values there are. So the PMF would be my possible values. I can get 0, 1, 2, 3, 4, 6, and 8. How many zeros do I have? If I count them up, I have 12 zeros. And how many possible values are there? Well, altogether there were 64 minus the 8 I've said cannot happen. So that's 56 values. If I count up the ones, I also get 12 of them. If I count up the twos, I also get 12 of them. If I count up the threes, I get 8 of them. If I count up the fours, I get 8 of them. If I count up the sixes, there are only 2 of them. And there are 2 8s. And that is my PMF. So this is the PMF we just worked out. Is it a true PMF? Well, add up all those probabilities and you'll find you do get 1. So yes. Now we want to find the expected value of this. So that was the average score people will get when they play this game lots of times. So we want to add up the score multiplied by its probability and add them all up. So that's going to be 0 lot 12 over 56, 1 lot of 12 over 56, that gives which gives altogether 120 over 56, which is 15 over 7, or about 2.148 something. So we're around about by here.